In July 2026, SpaceX released the technical specifications for its AI-1 satellites, the first concrete hardware in a project it calls Starmind. The goal is straightforward: move high-performance AI compute off the planet and into orbit, where power and cooling constraints that are tightening on the ground simply do not exist in the same form. Each AI-1 satellite is built around a compute payload of 120 kilowatts average and 150 kilowatts at peak. That output is roughly equivalent to a single modern, densely packed AI server rack on Earth. The satellite itself stands 20 meters tall when deployed and stretches to a 70-meter wingspan once its solar arrays are fully extended. Most of that span is solar array because the design must generate its own power continuously. The vehicle achieves a claimed efficiency of about 70 kilowatts of compute per metric ton, which is high for something that must also carry radiators, structure, shielding, and communications. The satellites are intended for a roughly 600-kilometer sun-synchronous orbit. In that specific orbital regime, the sun angle remains nearly constant, so the arrays receive illumination without the day-night cycles or weather interruptions that affect ground-based solar. Power generation therefore becomes essentially continuous, with no need to draw from terrestrial grids that are already seeing multi-year interconnection queues for large loads. Cooling is handled by 110 square meters of deployable liquid radiators. These panels reject heat directly into the vacuum as infrared radiation. The design claims roughly 1,400 watts per square meter of rejection capability, significantly higher per unit area than the systems used on the International Space Station. Redundant pumped loops and micrometeoroid shielding are included for reliability. On Earth, removing the same thermal load from dense AI racks typically requires substantial electricity for chillers, fans, or pumps, plus large volumes of water in many facilities. In orbit, the vacuum itself becomes the heatsink, and the energy overhead for cooling drops by roughly an order of magnitude. The satellites are chip vendor agnostic and modular. Early units are expected to fly with current generation NVIDIA hardware. Later versions can incorporate radiation-hardened processors from the Terafab effort that SpaceX is pursuing with Tesla. Because the compute section is designed to be interchangeable, the constellation can be upgraded over time without replacing entire satellites. High-speed laser links connect the satellites to each other, and results are downlinked through the existing Starlink network. The architecture therefore supports low-latency inference workloads distributed across orbit, rather than requiring every query to travel to a ground data center. Manufacturing is planned at a new facility called GigaSat in Bastrop, Texas. Prototype AI-1 satellites are targeted for launch in early 2027, with volume production ramping later that year. Starship is the intended launch vehicle because of the satellite's size and mass. Initial orbital operations are described as beginning around 2028, with the explicit aim of reaching gigawatt-scale AI compute capacity in space over time. The deeper implication is that this architecture directly addresses several physical and logistical limits that are becoming binding for terrestrial AI infrastructure. Large AI facilities on Earth face extended waits for grid connections, competition for land near fiber routes, community opposition over power and water use, and the thermodynamic cost of moving heat out of increasingly dense racks. By placing both generation and heat rejection in orbit, the design removes those particular bottlenecks. Sunlight arrives regardless of local permitting battles, and waste heat leaves as radiation rather than warming nearby water bodies or requiring cooling towers. One practical consequence is that scaling decisions shift. Instead of asking whether a regional grid can absorb another several hundred megawatts, or whether a community will accept another hyperscale campus, the constraint becomes how many of these large, capable satellites can be manufactured and delivered by Starship. That is still a difficult engineering and logistics problem, but it is a different problem from the ones currently slowing ground-based expansion. The approach also creates a clean separation between where the work happens and where the results are used. Inference can occur in sunlight, with physics handling the cooling, while the answers travel back to Earth through laser and radio links. Over successive generations, the satellites can carry newer, more efficient chips without requiring new buildings, new substations, or new water rights on the ground. SpaceX has framed the project as a way to unlock continued AI progress once terrestrial power and cooling constraints become the dominant limit. Whether the full constellation reaches the ambitious scale mentioned in some regulatory filings remains to be seen, But the AI-1 design itself already demonstrates a coherent engineering response to a set of problems that are growing more acute with every new generation of AI hardware. If you want more stories like this every week, like the video and subscribe. Drop in the comments what surprised you the most.